Hi, Vernon here. Welcome to my channel. In today's video, I want to do a comparison between QuadTrees and KD-Trees as they relate to generative art. So in the past couple of years, as I've been dabbling in generative art, I've used both QuadTrees and KD-Trees, and they have very similar purposes. Um, they look sort of similar, and that got me to thinking, which one performs better? Is there one that performs better in general, or are QuadTrees better in some situations and KD-Trees better in others? So that's what this video is about. Also, over the past couple of months, I've been building this new generative art framework in Go called Sketchy. So I thought I'll add each of these to Sketchy as um, in the API, so that myself and anybody who uses Sketchy can choose to use either. And as I'm implementing them, I'll run some benchmarks and put them through a sort of real world comparison. Um, so just to briefly go over the agenda here, I'll cover what QuadTrees and KD-Trees are, mostly through a demo that comes with Sketchy that's sort of a visual unit test for each. And then we'll look at the code between the two of them and use Go's built-in benchmarking to to run some synthetic benchmarks. That'll give us a first peek at which performs better. And then finally, we'll do a kind of a real-world generative art situation, and this is called the Jetpack Goat Algorithm. Really what we'll do there is we'll take a photograph and end up creating a single line drawing based on the photograph. So here is the end result. This is my cat Rory, and we'll show you how that's done, and then make that design, one with a QuadTree, one with a KD-Tree, and see how they perform. So to get started, let me bring up a terminal and launch these two kind of visual unit tests I was talking about. So these are both programs written in Sketchy. One is called QuadTree Demo, and the other, move this over here, the other is KD-Tree Demo. Oops, Jason. Okay, so far they look identical. And this is something I do when I add things to Sketchy is I write unit tests, but with generative art, you also need to run tests to see if things are visually looking how you'd expect. And so that's what this is for these two data structures. On the left, we have the QuadTree. On the right, we have a KD-Tree. So far, nothing to look at. So both KD-Trees and QuadTrees are useful ways of storing points in a 2D plane, especially when you want to be querying information about points in the plane. And so when I click on any of these demos, it starts adding points to the plane. And let's start with the QuadTree first and clear this. So in a QuadTree, each node has a certain capacity, and when you exceed that capacity, the default in this implementation is 4, then the entire region gets subdivided into 4 parts. So you can see this whole square now got divided into 4 equal parts. And once I add more than 4 points in some given region, it will subdivide again. And for example, if I just click in one area repeatedly, you can see it just keeps subdividing and subdividing. And then what this blue square is, this is one of the tests that it's running. This is a range query test. And this red number here is the number of points it detects in this range. So far, there's nothing there. But if I add points, the number increases, and then they're also highlighted in blue just to show that the test is working as designed. And then finally, the magenta coloring has to do with the other test it's running, which is a nearest neighbor test. And that's controlled by this slider. Right now, it's looking for, wherever my mouse is, it's looking for the 2 closest points in the quad tree to my cursor. And it supports any number of points. So now it's looking for the 8 closest neighbors. And so just by running this demo, I can verify that the quad tree is working as designed. So let's move over to the KD tree. It's very similar, but when we visualize it the same way we did with the quad tree, it looks quite different. So when we add a point, it immediately subdivides the entire region into either to the left, the rectangle to the left of the point and the rectangle to the right of the point. And if I click again, it's going to go in the this one divided it along the X direction. If I click again, it's going to divide it along the Y direction. And this kind of keeps going, alternating between dividing between X and Y. And it kind of has an interesting pattern. One of the things that this reminded me of, and I don't know if you all are old enough to remember this, but on Windows there was a game called Jetpack, and actually on KDE there is a similar game. Let me bring it up real quick. Let's see, it's called K-Bounce. So in K-Bounce or Jetpack in the old game, it's the same thing where you divide a region up horizontally and then vertically, and the idea is to remove some portion of the board. So that kind of reminded me of KD-Trees. And the range queries, so the points in this blue square, and the nearest neighbor queries, they work just the same in both the quad tree and the KD tree. So I'm not going to go deeply into exactly how the quad tree and the KD tree are implemented. There are actually much better videos for that. I'll have them hopefully shown above me, and then I'll have them linked down below. In particular, with the quad tree, the coding train did a 3-part series on quad trees. And there is also a computer file video that covered KD-Trees. So I recommend checking those out. So now that we kind of have this idea of what they look like and how they work, let's take a look at how they're implemented in Sketchy, and we can start kind of comparing how they're implemented, which one's easier. For the most part, they're very similar. So what you see here is, this is from the Sketchy source code. On the left, I have the Go code for the quad tree, and on the right, the similar code for the KD tree. And these, both the quad tree and the KD tree, are, as the name implies, they're trees, and the core of each is simply a node struct. So if we look on the left of the quad tree, there's a capacity. That's the number of points that each node can store. The default is 4. And then there is a slice or an array of points that this node holds. I call them, I have a convenience wrapper around a point, which is just an X and a Y value. I have a convenience wrapper called an index point, which holds a point and then some integer. And this becomes very useful, especially in the nearest neighbor query, and allows you to just add some extra information to the point. Each quad tree also has a boundary, and this corresponds to those squares that were drawn in the demo. And then there are pointers to 4 other trees, which represent the 4 subdivisions within a region. If we look over at the KD tree, you'll notice some similarities. We're still storing an index point, but here there's no capacity. Each node just stores a single point. When I was reading through the literature and how others implement KD trees, there's actually a bunch of different ways that people do it. This just seemed like the most straightforward, 1 point per node. There is also a region, which is the same thing as the boundary in the QuadTree case. And this would correspond to the region of that point before it gets subdivided into either the left or the right or the up or the down. And those subdivisions are what are listed below as left and right. So the two big differences here are a KD tree is a binary tree and a quad tree is a 4-area tree. And then in the case of a quad tree, we store more than 1 point per node. All right, so let's collapse those and just look at the different methods. So this is what, if you were programming in Sketchy and you wanted to use a quad tree or a KD tree, these are the methods you would call. And then, by design, they are pretty much identical. There are methods to add a point to a tree. So this is insert, and then search. So this says, does this point exist in the tree? And it's not comparing the actual index point in memory that's in the tree, but rather does the X coordinate and the Y coordinate of this point match some point that's already in the tree. Update index is almost identical to search, except when it does find a matching point, it will update its index with a value supplied into the function. And this is what allows you, for example, to when you're implementing some design and it's dynamic and you're drawing some line between a bunch of points, you can update this index as a way of saying this node has already been visited, or some other useful piece of information like that. The query function is what was going on inside that blue rectangle in the demos. You give it a rectangle to search in, and it will return all the points, if there are any, in the quad tree that are inside of that rectangle. A typical use for this would be, for example, if you were drawing a flow field and you didn't want any of the lines to overlap, or you wanted the lines to be evenly spaced. Or for another example would be if you're doing circle packing or some kind of polygon packing, you want to test a region to see, hopefully, to see if there are any points. If there aren't any points, then you can add your circle or your polygon, and maybe let it keep growing and keep checking until you get the maximum size without it overlapping anything else. The nearest neighbors was also shown in the demo. Just given some point in the plane, often this is this is your cursor if you're making it interactive. It will find all the points it'll find the K points that are nearest to that. And then just some typical things you would expect from any data structure, a way to clear it and start over. a method size to tell you how many points are in the tree, and then some Sketchy specific functions to actually draw, to draw the quad tree. This is more for diagnostic purposes, but this was used in the demo to actually show the regions and show the points. And that's essentially it. There are some kind of internal functions, but they're pretty simple. There are some things that are you might notice are missing. There's no remove method. In practice, when I use these type of things, I never really need to remove a single element. So I didn't implement that. And there might be some other things that aren't implemented for you to call it, complete, but for generative art purposes, it has everything it needs. So let's take a look. Besides performance, one of the other criteria I wanted to consider when comparing these two trees is ease of implementation. So the ease of use is, you can see kind of just from these functions from the end user, they're exactly the same. But as I was building each of these methods, there certainly were some differences. So let's look, for example, at the insert function. First, we'll look at the quad tree. The one thing I found overall is that the quad tree is very intuitive. Just from looking at the demo, it's very easy to understand what it's doing, why it's subdividing, and you kind of automatically have an idea of, if I had to go implement this from scratch, it would be fairly straightforward. And you can see from the insert function, it's not very complicated. Given a point, first it checks, is the point in my boundary? If it's not, then we can't insert it here. If it is inside the boundary, then you look at the node's array, and you ask, is it at its maximum capacity? If it's not, then put it in the array. And if it is, then we need to look in one of the subdivided regions. But there might not be any subdivided regions yet, so that's the next check. If there are no subdivided regions, then go ahead and subdivide it, and then recursively call this insert function into each of the 4 subregions. And that's it. Let's look at the same insert function on the KD-Tree. So I actually had to have a helper function down below. Insert. Let me actually totally expand this. Okay. So you can see it's much longer. So with the insert, we actually need an extra piece of information besides just the point. We need this integer d, which stands for depth. So it starts out the same. If the one point that the node stores is nil, then that means this is essentially a root node. So just set the point and we're done. If it's not, then we need to traverse down the tree to figure out the right place to put this. And that's where the depth comes in. Because if you remember from the demo, for each level, we alternate between whether we're splitting the region along the x direction or along the y direction. So this says if the depth is even, then we'll compare the x coordinate. If it's odd down here, then we'll compare the y coordinate. And then within each of these, when we compare a point, this decides, do we need to go to the left subtree or the right subtree? And then for each of those, if the tree doesn't exist, we need to create it. If it does exist, then we need to recursively call this insert function on that node. So it's not difficult, but it does take a lot more lines of code to implement, and it's the type of thing where you can pretty easily get turned around And if you're anything like me, you're not going to get it right on the first try. This took some debugging. So overall, the implementation of the QuadTree is, I found to be more straightforward. Let's just look at one more method here. Let's look at the query method. So again, on the QuadTree, it's quite simple. First, we look at the input, which is the rectangle that we want to search in, and we ask if there's no overlap at all between this rectangle and the QuadTree's boundary, then we're done. Otherwise, we look at each point in the node, and if the rectangle contains it, then we append it to the result list. And then we repeat the same process on each of the subtrees, if there are any, and we just keep appending the results, and at the end we return it. So it's very simple. Let's look at the same thing on the KD-Tree. So just like so it looks simple right now because nothing is expanded, but let's expand it. So it's similar in concept, but in order to in order to do everything right, there's just a lot more lines of code. There's a lot more kind of depth. But in the end, it's doing the same thing, but a little harder to implement. All right, so I think that's probably enough looking at code. So let's look at benchmarks now. One of the things I love about the Go language is that benchmarking is built in. It's just part of the unit tests. And so I'll give you an idea of what those look like. Let's go to the QuadTree test. These are pretty much the same for both the QuadTree and the KD-Tree. So this is the unit test and the benchmark for the QuadTree. So there are some typical unit tests for the different operations. Let me make this a little bigger. So let's scroll down to one of the benchmarks, and they tend to start with benchmark, and what you do is you give it a list of test cases that are usually listed as a bunch of a list of structs, and then each struct has just the variables that we need to build whatever state we need to build before actually running the benchmark. So this is putting together a bunch of test cases, and we're setting all the different random number generator parameters, the noise, the size of the size of the trees, size of the boundaries, and then in the actual meat of the benchmark, we have this b.run, which sequentially runs each of these benchmarks, and the core part is here. So reset timer, that means that all this stuff that took a while to set up, let's not count that time. We really just want to count the time of whatever's happening within this for loop here. And so, for example, in this for loop, it's for each of these different test cases, it's creating a quad tree and then inserting a bunch of points. And then we have the same thing for queries and nearest neighbor. And I'll show you what it looks like when it's running. Go to Sketchy. It's a little bigger. Okay. So I think I have this saved. All right. So when you run the the go unit test command, you can pass it some filters. So this is going to only run the tests that match the pattern tree and KNN for the nearest neighbor test. And it's also going to, in addition to latency results, it's going to also give us some memory statistics. So let's run this. So you can see that as it's running, it tells us the name of the test. It tells us how many times it had to run that internal for loop. It does that kind of automatically. And then it gives us the performance metrics that we care about. Specifically, the main one here is this column. This is the latency per operation, and that'll be the primary metric that we compare. And the other two columns are the memory statistics that we asked for. So how much memory was everything taking up, and how many times did memory have to be allocated. All right. So I ran this test previously, and then I compared all of these latency results as kind of a first measure of which tree type performs better. So let's take a look at those results. Okay. All right. So this is a lot on one page, but this is we'll go through this kind of sequentially. So from top to bottom, it's comparing, it's showing what operation the quad tree was being benchmarked with. So insert, query, or nearest neighbor. And then from left to right, it shows what the sample size was, how many points were in the tree. So we went from 1,000 to 10,000 to 100,000. So let's start by looking at the query performance. So the first thing to point out here is, so the y-axis is latency. You can see the units on top. So it's either microseconds or milliseconds. And so since this is latency, lower is better. And what you can clearly see from all three of the charts is that the quad tree performs significantly better than the KD tree. It requires a lot less time to perform the same number of operations. Specifically, if we just look at this as kind of a factor, the KD tree took more than 3 times as long to insert the same amount of points compared to the quad tree. And then that factor grew as the number of points increased. So you can see with 100,000 points, it's more than 4 times as slow. All right. So this could have something to do with just the complexity of the code required to implement the KD tree, and the fact that it has to do a lot more time traversing than in the case of the quad tree. So let's look at the query performance. Here, it's the same overall message that the quad tree performed better, but the KD tree was not as slow. In this case, it was almost exactly twice as long to do the queries as for the quad tree. And then lastly, let's look at the nearest neighbor. And you can see that for a small number of points, they perform very similarly. In fact, with 1,000 points, the KD tree was only 3%, only took 3% longer than the quad tree. But the gap did grow, pretty dramatically as the number of points increased. And I realized I should have explained this right away, but what's the difference here between uniform and noisy? And that has to do with the way that the points were allocated in space. So for the uniform case, before picking when it picks the points to put into the tree, any point in the rectangle is equally likely. And in the case of noisy, it's using open simplex noise as a way, with a certain threshold on that noise at any given point to determine if we're going to include the point or not. And the end result is that there are some regions which are very sparse and other regions which are very dense. And it tends to look a little more realistic. So I thought testing both cases would be interesting. All right, so for the benchmarks, it's clear the QuadTree is the clear winner. The last question is, do we see the same sort of performance difference in a real world scenario? And that is what we'll talk about now. And to kind of motivate this, let me run this program. It's based on my very handsome cat. This is Rory Jetpack. Let's see. Okay. So I said at the beginning that this is called the Jetpack Goat demo. And where I heard about this algorithm was a TEDx talk. I'll have it linked and hopefully on the screen right now. And there, this man, his name is John Proudlock. He gave a talk called "Can Virtual Goats Make Real Art?" And I don't think in the talk he actually gives his algorithm a proper name, so I just call it the Jetpack Goat Algorithm. And if you want to know why, definitely go watch that talk. But the idea is, if we take something like a photograph and we convert it to a set of points, can we connect all those points with a single line in a way that looks interesting? And then, we can plot that. That's what he did. He makes his own plotters that plot along a vertical surface. In my case, I'm using my AxiDraw plotter. So this is a picture of my cat. And just as an aside, you can see that this doesn't really look like a photograph. Here is kind of a trick. And especially if you are a plotter artist, this might be useful to you. So let me bring up the original photo of Rory. So this is Rory. So he's a very handsome boy. So I'm going to open this with GIMP so I can edit it. So this is kind of a technique that I just stumbled upon. When you want to, the problem with photographs and plotting is there's just way too much information in the photograph, even grayscale. We want to really reduce this. So one way to do that is to apply some edge detection. So starting with a photograph doesn't have to be grayscale already. In GIMP, if you go to filters and then it's edge detect, and all of these can work, but I typically do with the second one, edge. You can see that it, besides pulling out the edge, it also just pulls out some of the parts that might be nice for the plotter to sketch. So I usually just kind of slide through these options and see which one works best. Let's try this, the Sobel algorithm. And then the last step is just to invert the colors. and then save that as a new image. So this, rather than the original photograph, has a lot less information, easier to then use in your code to filter on things, which I'll show you now. So in this Sketchy program is loading the picture, and then you can see that the dots are kind of all over the place. Right now, what it's doing, and this is pretty common in generative art, is we want to filter on some aspect of each pixel, and often that is the brightness or the luminosity. And so that's what this is doing. And that's what this luminosity slider controls. Goes from, one means it's not filtering anything. And so that's why the points are kind of randomly scattered. The other thing is that there's another slider, probability, that says even if it matches or passes this luminosity filter, I only want to admit that point this percent of the time. So even though there's no current filter on luminosity, there's only a 3% chance that any point is going to show up, and that's just because otherwise you would end up with way too many points. So now this is kind of the fun part where you play around with these variables. So mainly just the first, like the luminosity, and this will show me where the points are going to be. I pretty much just want to capture Rory's face, and I also can increase the probability, and there's just a matter of just finding something you like, and then you might see scrolling down here, each time I make a change to the parameters, it tells me how many points are on screen, and that is useful for kind of benchmarking the actual when we launch this algorithm. So I think what I settled on for this picture was 95% luminosity, and then 25% probability. Yeah. And so this gives us roughly 27,000 points. And then this last slider here, points per tick, this controls, when I launch this algorithm, this controls how many points is it going to consume, each frame. And that just controls the animation and how long the overall thing takes. But so here's where the actual Jetpack Goat algorithm comes into play. When I press that button, this is going to repeatedly do a bunch of nearest neighbor tests. It starts with a point. It starts at the origin, which in Sketchy is the bottom left, and it asks which point is closest to the origin, and it's probably going to be this one. And then it marks that point as, okay, I've been visited. Where's the next closest point to this one? And then it marks that one as visited, and adds all these to a list. And in the end, it's going to draw a line. So we're going to get a single line that connects all 27,000 points, and it's going to go from nearest neighbor to nearest neighbor. So I thought this would be an interesting test where side by side we can show how this would perform with a KD-Tree as the backing data structure versus a QuadTree. So let me show you that. I actually have a video. I recorded this earlier just because it was tricky to set up. All right, let me pause this and go full screen. All right. So on the left is we're using a QuadTree, and on the right we're using a KD-Tree. And then when I play this, the first thing, let me just play it and talk as it's going. So the first thing I do is I remove the actual image in the points because I only want to time it doing the actual nearest neighbor part. And so as fast as I can, I try to click both buttons. It doesn't have to be exact because in the terminal below it shows the results, but you can see on the left it's doing these nearest neighbor searches and connecting the points. And you can see it's going faster than the KD-Tree. And eventually you'll see it finish. And then on the terminal on the bottom left, you'll see kind of the results. So it took, 27 seconds. The KD-Tree is still going. I'll pause it once it stops so we can compare. It's almost done. All right, so they're both done, and you can see the performance metrics in the terminal. With the QuadTree, it took 27 seconds. With the KD-Tree, it took 49 seconds. And then, if we want to compare to the benchmarks where we were comparing latency, that is the very bottom row. So this, the milliseconds per point was, conveniently 1 millisecond for the QuadTree and 1.82 for the KD-Tree. So that's a 1.8x slower result for the KD-Tree, which is pretty much in line with what we saw on the benchmarks. But I think the important part of doing this real world test is there's a lot more going on than just in this case the nearest neighbor search. The underlying the game engine that Sketchy uses, Byton, has to manage its draw and update loops, and then the 2D drawing library that Sketchy uses, Canvas, has to manage taking this list of points and then drawing them into memory, and then Byton has to take care of actually drawing that onto the screen itself. So it's hard to say exactly how the performance would translate from a purely benchmark case to the real world, but overall the QuadTree was the definite winner. But I should add as a caveat that this is a pretty narrow case. This is 2D generative art. One advantage that the KD-Tree has is that it generalizes to an arbitrary number of dimensions. And where that's especially useful is in things like databases. Consider if you had in a relational database, you had some table that had a bunch of columns. Each column is like a different dimension. And if you had some SQL query where you're selecting a bunch of columns, but you also have a bunch of where clauses that restrict the range of each column, that's analogous to that 2D range search that we did in the demo, but it's in an arbitrary number of dimensions, a very high number of dimensions, and that can really speed up the queries. QuadTrees don't have that same obvious scalability. There's a 3D version of a QuadTree called an octree. That's kind of as far as it goes. So overall, I hope you liked this video, and if you did, I definitely suggest you check out the other videos that I have linked below. And if you're interested in generative art, then and you like the Go programming language, then check out my Sketchy generative art framework. Thanks.